You've probably seen a robot arm pick something up, right? It looks so smooth, so simple. But what's really going on under the hood? Well, it turns out it's this incredible dance of physics, planning, and control all working in perfect harmony. So today, that's what we're going to do. We're popping the hood on a complete pick-and-place system to see how it all really works. And that brings us to the big question, right? How do you actually teach a robot to do this stuff with any kind of precision? I mean, it's so much more than just moving an arm around. We're talking about making a machine that can touch, feel, and handle objects in its world reliably. So how do we build it so it can grab something, not drop it, and put it down exactly where it needs to go every single time? Okay, here's our game plan. We're going to tackle this piece by piece. First up, we'll look at the gripper design itself. Then we'll dive into the nitty-gritty of tuning the physics of touch. After that, it's all about how the robot plans the perfect grasp, and the state machine that runs the whole show. And, of course, we'll wrap up with some hard-won lessons from the trenches. All right, let's start with the most physical part of this whole system, the hand. In our case, it's a custom-designed parallel jaw gripper. And let me tell you, before you write a single line of code, you have to get this part, the physical design, absolutely perfect. And here it is, maybe the single most critical rule in all of robotic grasping. It sounds almost too simple. Your gripper, when it's fully closed, has to be smaller than the thing you're trying to pick up. For our 40mm box, our gripper closes down to 38mm. That tiny 2mm difference, that's everything. That's where all the magic happens. And this really hammers home our first big lesson, a real senior engineer kind of tip. You could have the most brilliant, complex software in the world, but if your hardware is physically incapable of grabbing the object, well, you've got nothing. It sounds so obvious, I know, but you would be shocked how easy it is to overlook this. Okay, so our hardware geometry is solid. Now we can jump into the virtual world. But here's the catch with simulations. For them to be worth anything, the physics have to feel real. We have to meticulously tune our physics engine, MuJoCo, so that when our virtual robot touches something, it behaves just like it would in the real world. First up is this parameter called condem, or contact dimensionality. We've set it to 4. Now, why 4? What's the big deal? Well, that fourth dimension is torsional friction. Think about it. Without that, as soon as the arm starts to move or rotate, the box would just spin around between the fingertips like a pinwheel. This one parameter is absolutely critical to keep the object stable during transport. Next, let's talk friction. See that first number, 1.5? That's our sliding friction, and yeah, we've cranked that up on purpose. That's what gives us the raw gripping power, the squeeze needed to lift our 150-gram box against gravity. The other two values are way smaller. They're just there to provide a little bit of damping to stop any unwanted spinning or rolling. Okay, now for solref. This basically controls how stiff a contact is. We're using a tiny time constant of just 2 milliseconds, which is incredibly fast. What this means is, the moment the gripper touches the box, the contact force builds almost instantly. It creates a really solid, rigid connection. You know, it's the difference between grabbing a brick and grabbing a sponge. We definitely want the brick. And finally, SolImp helps us fine-tune that rigidity. These values create what are essentially rock-solid contacts. They reach maximum stiffness after the gripper has penetrated the virtual surface of the box by just 1 millimeter. Putting all these parameters together is what gives us a stable, predictable grasp in the simulator that we can actually trust. I love this table because it just lays out all the trade-offs so clearly. It's basically a cheat sheet for tuning these physics parameters. See? If your sliding friction is too low, boom, the box slips out. If your contact is too soft, the box will vibrate and jitter in the grip. It's a total balancing act. You need everything to be stiff enough to be realistic, but not so stiff that the simulation becomes unstable and just breaks. With our physics of touch all dialed in, we can move up a level to the robot's brain, the motion planner. This is where the system does all the heavy lifting, computing the precise joint angles it needs to position that gripper perfectly for the grasp. So before the arm even twitches, the planner is already hard at work. It uses an algorithm called inverse kinematics, or IK, to figure out 4 critical poses. It calculates the pose for approaching the box, the pose for actually grasping it, one for hovering above the target, and finally, the drop-off pose. Planning out all these keyframes ahead of time is essential for a smooth, predictable motion. And the precision here is just phenomenal. Get this. The IK solver is able to find joint configurations that place the gripper's fingertips within less than 1/10 of a millimeter of the target.
That's thinner than a sheet of paper. It's subhuman accuracy, and it is absolutely vital for making this whole thing work reliably.
But even with that incredible precision, we hit a classic robotics bug. The IK solver would report, "Success, I found a solution." But when we looked at the simulation, the gripper was pointing completely the wrong way, rotated a full 180 degrees. So the math said everything was fine, but the physical result was a total failure.
So, what was going on? Well, the way we were calculating the orientation error had a mathematical blind spot, a singularity at exactly 180 degrees. The fix was to switch to a different mathematical tool, pen.log3, which handles all rotations cleanly, including those tricky 180-degree flips. And let me tell you, this is one of those expert-level details that can save you days of debugging. Okay, so we've got the hand, we've got the sense of touch, and we've got the brain. Now we need the nervous system to tie it all together. This is the job of the state machine. It acts like the conductor of an orchestra, orchestrating every single action in the perfect sequence.
And here's a key principle of good engineering in action: you build on a solid foundation. This complex project wasn't built from scratch. It integrates robust, well-tested components from previous work. Things like impedance controllers for smooth motion and the RT-Star motion planar for generating collision-free paths. You always use what works. This timeline shows the first 6 of the 11 states that make up a single grasp, and you can see the logical flow, right? Plan the approach, execute the approach, descend straight down, close the gripper, lift straight up, and then, and only then, do you start planning the transport move. Each state is a discrete, manageable step in a much larger, more complex operation. And now for my favorite part, the war stories. This is where the most valuable learning happens. Down in the trenches, debugging those real-world problems that you just don't find in textbooks. So, bug number 1. The gripper would touch the box and just bounce off. The contact was weak, it was intermittent. The cause? The position actuator just wasn't strong enough. Its spring constant, its Kp value, was way too low. The fix was simple. We quintupled its stiffness, giving it enough force to really push into the box and establish a firm, stable contact. Next up, we saw the arm drifting away as the gripper closed. The very act of squeezing was pushing the whole arm away from the target. Turns out, we were only compensating for gravity, which wasn't enough. The fix was to engage the full joint impedance controller during the squeeze, actively holding the arm's position and resisting those contact forces. And this last one? Oh, this is a classic. The gripper was just crashing right into the table. Why? Because the single constant, the offset from the robot's wrist to the fingertip, was off by just 15 millimeters. A tiny measurement error, barely more than half an inch, was causing the entire system to fail catastrophically because it was targeting a point inside the table. And that's really the perfect takeaway, isn't it? It shows how a tiny, seemingly obvious detail can completely derail a massive software effort. It really makes you think. So, I'll leave you with this question. What's the one seemingly obvious, simple detail that you'll be sure to double-check first on your next project?